Hey guys, this is going to be a recorded solution to Unit 1's free response question number 1. I've had a lot of questions on it, so I'm going to go over it again. Alright, so on this question, we've got a scenario where we've got a truck and a car that crosses this line at x equals 0. And what it does is it says that the car is stopped right here. So here's your little stopping line. The car is stopped, and the truck is actually moving, but it's back here somewhere. And so what it says is that at time t equals 0, the car starts moving and travels with a constant acceleration. So the car just starts like normal, push on the gas, and starts to accelerate to the right here. Okay, but at the same time that that car starts going, this truck has come up and just timed it just right to where he starts at the exact same place at the exact same time, but he's already moving. He's got this velocity vt, and that's a constant speed. It specifically says it's a constant speed. Now, because that truck's already moving, he's going to be zooming past this car. And eventually, though, the car, because it's accelerating, maybe got mad or whatever that the truck passed them, the car steps on the gas and accelerates and catches up to the truck whenever they both get to this position in front of this house, x equals d. So the truck is here and the car is here at the same time. And so on this question, we're asked what happens with these two cars, what their speeds are, their accelerations, their positions. And so let me go through that real quick, and I'll kind of explain a little bit a different way to kind of go about it. All right, so let's start off with the first one. It says to sketch and label the graphs of the velocity of the car and the velocity of the truck as a function of time. Indicate any important velocities or times. Okay, so the time when it crosses the house, that's an important time, TD. That's the time such that a time TD is that they're at the same place. And also, I'm going to indicate on here the velocity of the truck. That's how fast the truck's going. And just to make the scaling right, I've got kind of like, this would be like half the velocity of the truck, 3 halves the velocity of the truck, 2 times the velocity of the truck, and so on and so forth. All right, so first thing you want to do is graph the velocity of the truck. All right, so because that truck is moving at a constant speed, a velocity time graph would be a straight line, right? So I'm going to come up here with a ruler, and I'm going to graph the velocity of the truck as a function of time. So that's going to be some kind of a straight horizontal line at vt. All right. So that's the velocity of the truck. Now, in order to find the velocity of the car, we kind of got to make some kind of get some understanding of what's going on here. So first of all, we know that the car is accelerating with a constant acceleration. So on a velocity time graph, a constant acceleration would be represented by some kind of a straight line, starting at the origin because the car starts at rest, so the initial velocity would be down here, and it's going to be at some kind of a constant velocity or a constant acceleration graph, so it'd be a linear kind of graph. Now the problem is we don't know where this thing is going to intersect, but we can get some information from the graph that we already drew. So if you remember that if I want to find a displacement, I can get that from this velocity versus time graph by taking the area underneath the graph. All right, so let's look at the truck. I'm going to take the area under his velocity time graph, and we don't know numbers, but we can just kind of do it in terms of these little tick marks down here. So this area underneath this thing is just the area of a box, so that'd be the base times the height, which would be 1, 2, 3, 4, 5, 6 across the bottom. That'd be the base, and then the height would be 1, 2. All right. So we could pretend that this would be 12 meters. All right, the displacement. We're just going to kind of pretend that this is 12 meters. It's obviously going to be longer because it's on a road, but that's how far the truck has traveled in this amount of time. All right. So in order to get the graph of the car, we need to understand something about it. It says, but the car later catches up to the truck in front of the house such that at a time TD in front of the front of each vehicle is at a position TD. So right here it says that whenever these two things meet, they've traveled the same distance. The car has traveled the same distance as the truck. So that means that whatever graph I draw of the car, it has to have the same area as what the truck had, which is 12 meters. So let's work that out. The area of the car, okay, in other words, the displacement, has to be 12 meters, okay? Well, earlier I said that we have to have a triangle, or a linear function, a linear function to have a constant acceleration. So what's the area of a triangle? Well, that's 1/2 base times height. Well, the trick here is that we know that the time at which they meet is the same for each car. So that means that wherever this car goes, whatever time it's going to take the same amount of time as the car. So that means that the base term of this is like the time on this graph, time has to be the same. So in this graph, it's 1, 2, 3, 4, 5, 6 units of time. So that has to be 1/2 times 6 times some kind of height. All right. So if I line up my ruler here, whatever this area is, I don't really know. I'm just kind of drawing in a triangle. Whatever this area is, this height of this triangle has to be has to be a value so that I can make this equation work out. So I'm going to set these equal to each other. 12 has to be equal to 1/2 times 6 times the height. And when you do the math here, you work this out. You move the 1/2 over here, so I'm going to multiply by 2, divide by 6. So 2 times 12 is 24, right? And so that means 24 divided by 6 is 4 units. Okay, so the height has to be 4 of these little tick marks. So 1, 2, 3, 4. Okay, so here we go. So when I draw my graph for my car, I have to have it end over here at time t equals d with a velocity of 2 times the velocity of the truck. And so now, when I calculate the area of this red triangle, okay, if I come over here and I say, well, what's the area of this triangle? It's going to be 1/2 base times height, 1/2 times 6 units of time times 4 units of height, and that's going to be equal to 12 meters. And so sure enough, the displacement of the car, this red one right here, has moved 12 meters, and the truck has also moved 12 meters. So that means, for this first part, that the velocity of the car has to be equal 2 times the velocity of the truck. That's really pretty key at the house. Whenever they reach the house, that's the condition that we need to know. And that's pretty critical to the rest of the problem. All right, so the second part of the question talks about these two students talking about how the speed of the car and the truck compare. Well, the first student says the distance traveled by the car and the truck are the same. That is a correct answer. That is correct. Okay, because it says it in the problem. They've both traveled a distance d. Now, it does say the time is the same, so they must have the same speed. Okay, the time is the same. It says it in the problem. They both pass the house at the same time. That's also a correct statement. An incorrect statement is where it says they must have the same speed. That's incorrect. All right, and the reason why is just think about it in terms of the graph you just drew. the velocity of the car starts from 0 and ends up at 2 times the velocity of the truck. So just from the graph that you drew, that's enough support to say, well, no, his statement is incorrect, because they obviously don't have the same speed at the end. You could also say that, well, the car is accelerating from rest, and so in that time, the velocity does change, so they can't have the same speed. All right. Now, student 2 says, I don't see how that can be. The car catches up to the truck. That's a true statement. The car does catch up to the truck. So the car has to be going faster. Well, that is a true statement. It's a true statement because that feature of that graph, whenever we looked at it, we said, hey, at time TD, the velocity is twice as much as the truck. All right, now part C says, let's derive an expression for the acceleration of the car. Express your answer in terms of d and vt. Okay, so this is where you're going to use some kinematics, because we know that the car is accelerating at a constant acceleration, so we can use kinematics. And so I'm just going to say, I'm going to go back to this kinematic equation, v squared is equal to v naught squared plus 2a delta x. All right, that's our kinematic equation. And all I need to do is just substitute terms in that's given to us. All right, so what I'm looking for here is a. All right, now, first of all, I know that the initial velocity of the car is 0, so that term goes away. I also know that the velocity of the car was 2 times the velocity of the truck. All right, so that's where it says express your answer in terms of d and vt. That's how I get the vt in there, because I know when I get to the house, the velocity of the car is 2 times vt. So this velocity of the car term right here, I'm substituting in 2 times the velocity of the truck. All right, and we'll get a square. Now, on the right-hand side of the equation, a will be the same thing. It's just a, but the delta x is how far the car traveled. Well, that's d. All right, so let's go through and rearrange this equation, do the algebra and solve for a. So I've got a 2, but that's squared, so that's 4. Velocity of the truck is squared, and that equals 2a times d. I can divide by 2. Divide by 2, this goes away to 2. Divide by d, I'll have a d down here in the bottom, and so that means that the acceleration is equal to 2 times the velocity of the truck squared divided by d. And that's your solution for part C. All right, and now the last part says determine the time at which the speed of the car is equal to the speed of the truck. All right, well, I think that you can just verify that from the graph. All right, so from the graph, it's pretty clear that there's a specific time when the speed of the car, that's the red line, has the same speed as the speed of the truck. And that's right here where the two graphs intersect. And so if you've scaled your axes appropriately and you drew this out right, where does that occur at? It occurs right here at time of d divided by 2. It's half the total time. And so the car's speed is twice the truck speed, so therefore they're equal at half the time. And that's the solution for part D. All right, guys, I hope that helps. If you have any other questions, just email me, let me know, and we'll go over it. Thanks a lot. Bye-bye.